Up here, first of all, I'd like to thank the University of Missouri, especially Dr. Duncan and his staff, Gloria Smith, and others who arranged this and set up all the support. What I'm going to talk about today is 20 years of history and research that we have been performing in this area. We currently call it low-energy nuclear reactions. That may not be any more accurate than the term cold fusion, but it's one that the field has kind of adopted. We're going to do a little bit of tag team. In addition to myself, Dr. Pam Mosier-Boss is going to be doing part of the presentation, and also Larry Forsley is going to also be involved. And we are including work that has been done by Melvin Miles and Mitchell Schwartz in the presentation. Right off the top, I'd like to offer a little bit about how do you survive 20 years in this controversial field. And Dr. Duncan talked about the importance of following the scientific process, and that certainly has served us well. Carefully design experiments and conduct those experiments, repeat and validate the results, submit those results to peer review, respond to the referee's comments, and publish, and then based on that design new experiments and continue to advance the progress. By doing this, we've essentially been hiding in plain sight. We have 23 peer-reviewed papers and 2 articles in New Scientist, plus National Public Radio did a feature on our work, numerous web-based articles, and most recently the Discovery Channel Brink did an article on us. And throughout all of this, the reception that we have received certainly was much better than what Pons and Fleischmann received when they made their announcement. And in fact, there at the bottom you see some of the most recent remarks. Bob Park, who wrote Voodoo Science and has been very skeptical of cold fusion, is now admitting that this is science. Johann Frenge from MIT, who's in the hot fusion group there, after looking at our results that were presented at the ACS meeting in March, in a quote in a New Scientist article, said the data and their analysis seems to suggest that energetic neutrons are being produced. And your very own Rob Duncan said this is not pariah science anymore. So anyhow, a lot of things have changed in the last 20 years. Going back 20 years ago, here was the situation in March of '89. Pons and Fleischmann made their announcement. The physics community said, hey, their experiments aren't repeatable, there aren't any refereed papers, the experiments haven't been replicated, and if it's nuclear, where are the neutrons? These are probably some of the politer comments made. For those of you who are around then, comments, if this is really nuclear, we don't need a calorimeter to determine that it's nuclear. If it's really nuclear, where are the dead graduate students? There were several comments like that. But in spite of all that, thousands of scientists worldwide attempted to replicate the results. And after all, Pons and Fleischmann were both very respected scientists. I think the Time magazine kind of got that right here when they said it stirred excitement and outrage in the scientific community. And I probably don't need to tell you this, you probably know it, but just to remind you a little bit, why some of the controversy between the chemistry and the physics community, and it's shown here. Chemical reactions typically liberate less than 5 electron volts per atom. Nuclear reactions are millions of times more energy per atom than chemicals. So when you had chemists standing up saying we're seeing 30% excess energy, it just how do you get there? It was just too far of a bridge to cross to get up to nuclear reactions, particularly with the other problems that they have. A lot of people went into the labs to try and do these experiments, as I indicated. And the Fleischmann-Pons approach is shown here on the left. A lot of things, we kind of think we understand why some of them failed. For one, was they may not have had the palladium rod completely submerged, and what would happen is the deuterium would load in the solution and then diffuse up and diffuse out into the atmosphere, so you never did achieve the loading in the palladium. The history of the palladium was unknown. In a lot of cases, a lot of universities, you found a chunk of palladium, you decided, well, let's use this without any knowledge of what was the real condition of that palladium. And the other thing is lack of recognition that there was an incubation time of several days to several weeks before the reaction would display itself, and most people didn't understand that. At Speyer System Center, we devised another technique to do the experiment. Dr. Stan Spock, who was an electrochemist, he and Dr. Boss were working in developing high-energy density batteries for torpedo propulsion at the time. And they said, you know, rather than try and load a palladium rod, let's start with palladium chloride and a lithium chloride solution in deuterated water. When we apply a current, what will happen is the palladium will plate out on the cathode, and as it turns out, that's also where the deuterium will evolve. So what we were doing is we were loading the deuterium into the palladium as it was being built up on the cathode. And in the picture there in the upper right, you see the structure of the electrode after we took a look at it with a scanning electron microscope. You see a very cauliflower type approach, a lot of surface area. You know, they say if you have a choice of being good or being lucky, choose be lucky. I think in this case we were both good and lucky. Certainly it was a good idea to do this. We were lucky in that now we understand. I think we have a great more understanding that surface area is very important, and clearly this technique produced a high surface area. We have an understanding that defects in the lattice may be very important, and in this process we were actually building the defects in at the time. These were things we didn't necessarily appreciate at the time we devised the scheme. The main reason we did this was because we didn't want to wait 2 weeks. And so the advantages of co-deposition, short loading times with measurable effects, and you see 3 of the publications in general in the presentation. Whenever you see a reference like that, it represents one of the 23 papers that we've published. These experiments were extremely high repeatability. It maximizes experimental controls, and you'll see how we take advantage of that several times over the 20 years. And extremely high surface area and defects built into the lattice, as I've already mentioned. Here's an example that shows how fast we saw the reaction. You see there in the chart in the middle 2 experiments. One and in both cases the cathode was hotter than the solution. We had thermocouples, one affixed to the back of the cathode, one in the solution, and in a matter of less than an hour we were able to notice that the cathode was significantly hotter than the solution, or measurably hotter than the solution. That shouldn't be. Yeah, if it's joule heating, then the solution should have been hotter, and certainly the solution was higher resistance than the cathode. So, this was a surprise. This is something that we shouldn't have seen. Also, Pons and Fleischmann talked about a phenomena called heat after death, and we observed that also, where when we turned things off, you'd get a burst of energy, and so something was happening here that we didn't understand. We didn't do a lot of work with calorimetry, and for a variety of reasons, but one of our co-workers at also a Navy lab, Dr. Mel Miles, who was at China Lake, did some experiments using co-deposition and calorimetry, and again, so not only was he able to do this and achieve these results repeatedly, they also occurred very quickly, and he showed that the co-deposited cathodes produced excess heat equivalent to what was being produced by the bulk palladium cathodes. And in fact, he also talked about the positive feedback, another phenomena that Pons and Fleischmann had talked about. And you see on the left the expected behavior when the rate of excess enthalpy remains constant, and then you see on the right the positive feedback effect. Dr. Duncan mentioned a couple of times that every time we looked for heat, we saw excess heat, and that's correct. When we looked for heat, we realized we really didn't understand what was causing it, and so we have spent the bulk of our time looking for designing experiments and looking for results that would help us understand the underlying physics that are occurring. And one of the things that we did was we took an IR camera, we cut a hole in our cell, and by the way, here I have a typical cell that we use. It's costs less than $1 at a hobby store. This one already has the hole cut in it, and you put a Mylar window over that and then view it through an IR camera, And when you do that, you see the kinds of display here in the upper left. We were able to observe how the electrode heated up during this process. And so it wasn't just a gradual heating up of the whole electrode. There were spots that were occurring. Dave Nagel retired from the Naval Research Lab and now at George Washington University, who is also here today and I think going to be one of the speakers, did some calculations based on the size of the pixel size of these spots as they were, the flashes, looking at the energy being conducted away, and determined the bottom line was that the hot spots must be due to nuclear energy release. We took advantage of the co-deposition, and this is one of the examples in experimental flexibility. We showed the IR data to Lowell Wood from Lawrence Livermore Lab, and he said, hey, you guys in the Navy, why don't you put a transducer in your cell, because these should be leaving signatures. You should be hearing these. These appear to be mini explosives. Well, we're the Navy. We did one better. We took a piezoelectric material, co-deposited right onto the face of the piezoelectric material, which is shown here in the upper left. By doing that, we were able to get a direct input of these events when they occurred, and the two plots along the bottom show the kinds of results we would get. You get a very sharp pressure spike down, and then followed by a temperature spike that would then gradually decay, and the pressure spike would travel much faster than the temperature, and so as a result, we did some calculations, and based on this, we felt that this is an indication that in fact the reaction is occurring very near the surface of the electrode rather than in the bulk of the electrode. Other experiments that we did looking for nuclear signatures, photographic film. You see on the upper left, after we had conducted an experiment, and this happened to be with one of the piezoelectric material transducers, we dried it, put a thin piece of mylar or something between it and film, did this in a dark room, put it inside a dark envelope and left it for a few days, then took the film out and developed it. And when we did that, you can see that the film was fogged. We have other detectors, that a gamma ray detector and X-ray detectors. So we have seen other evidence of nuclear reactions. Low intensity radiation in this experiment you see on the right an X-ray and a gamma ray signature. These were conducted at the same time. They were on separate electrical circuits, and you can see that in fact the data seems to be consistent. They were both tracking, so that again this offers more positive indication that nuclear events are occurring. Tritium production was another thing we looked at, and published this in Fusion Technology. Did a very careful tritium experiment. One of the problems or one of the challenges in publishing papers that purported to produce tritium is that there's some tritium in deuterated water. And so how did you know that you in fact produced additional tritium? And it's even a harder case to make if you have to replace, if it takes a long time to do the experiment and you have to replace and add more deuterated water, or you're providing a natural enrichment of the tritium. The fact that our experiments occurred over a much shorter period of time made it easier for us to make the argument that no, that was not the case. And in fact, when we did these experiments, we had 3 out of 5 experiments we did produced tritium production rate that, if averaged over a 24-hour period, was between 3,000 and 7,000 atoms per second. 2 experiments showed a complete mass balance. Did not show any additional tritium. As you can see here, although we say it's 3,000 to 7,000 atoms per second over a 24-hour period, we really don't. The indication is that the tritium production occurred in bursts rather than at a uniform period of time over that time. One of the other things that we started looking at is the impact of an electric and magnetic field on the results. And in the cell on the left, you see we have 2 permanent magnets there, and just, they're strong enough that they hold themselves to the cell. In the cell on the right, we just taped, literally with Scotch tape, a couple of copper foil strips that were attached to a regulated high voltage source, something that we bought at a used electronics store for $7, I think, because this is a low budget operation. And when we did that, in the top center, you recall the surface morphology that we saw when we just did the co-deposition in the absence of either electric or magnetic field. In this case, you see the pictures in the electric field. You see formation of fractals, in some cases long wires, some folded foils, and even craters, which could indicate something relatively violent or something happened. A lot of energy could have been released there. These microvolcano-like features, that we see on the left in the applied electric field, in fact, also matched sonofusion of thin foils that Roger Stringham has done, and recall from the pictures that Dr. Duncan showed from energetics, the same kinds of things, and so this is consistent with what others were seeing in this field. And note the middle on the left, that looks like something where a high energy release, it melded the metal, it ejected it, and then it quickly recrystallized, because recall this is all underwater. If in fact you're getting this kind of reaction, then it would suggest that maybe there are other things that would be evidence of nuclear reactions, and one is there transmutation going on. And so if we took a scanning electron microscope with EDAX capability and put the crosshairs on the rims of the ejecta, what we found was significant examples of aluminum and magnesium, metals that were not there when the experiment was started. Here's another case where you can see magnesium, silicon, aluminum, and zinc. When we published this paper, it was in review for, I think, 7 months. Dr. Duncan talked about it's good to get harsh review. I think this one qualifies. It went back and forth several times, trying, with them forcing us to convince us that this was not contamination, that this wasn't there to begin with. And ultimately, we did several, blank and control experiments. We went back to them and finally pointed out that even if we had put aluminum in solution at the time the experiment started, it would not have deposited from an aqueous solution onto the cathode. And so at that point, they agreed and allowed it to be published. In a magnetic field, we saw similar things, except a much higher incidence of iron, as you can see here, and you can see how many of these little craters there are on the picture on the left. We weren't the only ones that were seeing transmutation effects, and in fact, Professor George Miley from the University of Illinois compiled a list of groups that were reporting transmutation, and you can see there are groups here in Japan, Italy, Russia, China, the USA, and again, a couple more in Japan. On the right, you see the number of labs, like 11 labs of these 15 reported. They were seeing iron, 8 said copper, 7, 6. And then on the very bottom, you see the materials that we were seeing. So you can see that we were also seeing some of the same results that the other labs were seeing. I think this is a particularly strong evidence because only ourselves and Bakras at Texas A&M were using co-deposition to do this. In the case of Japan, it was gas loading. In the case of Israel, it was, and they're not even on here, I don't think, it's the bulk loading. So the fact that all of these experiments are producing these transmutation results is I think, stronger evidence than if everyone did the same experiment and got these results, because this way no single error on the part of one or all of the various experimental groups could account for it. At this point, I'm going to turn over to Dr. Boss to talk about some of our high-energy particle work.
Okay. So in 2004, George Miley suggested to us that we should start doing some experiments using CR39 detectors. And so we looked into it and found out that CR39 is a polyallyl diglycylcarbonate polymer that has been widely used in the inertial confinement fusion field as a solid-state nuclear track detector. And its most common everyday use in our lives is that it's the lenses in our glasses. It's plastic in the lenses. And what happens is when a charged particle hits this plastic, it causes an ionization trail that's more sensitive to etching than the bulk. And after the experiment, all you have to do is just dump it into your etching solution, usually 6.5 normal sodium hydroxide at 60 degrees, and etch it for 6 hours. And then you have these tracks that look like pits on the surface. And these tracks have a conical-like shape here. Last year, a paper came out by Durrani discussing the weaknesses and strengths of solid-state nuclear track detectors. One of the strengths is that there's a small geometry, the trails of damage on the orders of nanometers or microns in diameter and length. Long history and selectivity of track recording. These solid-state nuclear track detectors can retain a record of the nuclear activity for billions of years. And that's advantageous in that when you can periodically look at your detectors from time to time to look for evidence of other reactions. There's an existence of a threshold for registration. You have to have a certain charge and energy for them to appear. These detectors are very rugged and simple to use. They're inexpensive. They have an integrating capability, meaning that when an event occurs, they're permanently stamped on the surface of the detector, so you don't lose anything. Everything accumulates, so nothing can get averaged away. And they respond to both charged particles and neutrons. The weaknesses, of course, is that it does lack real-time capability. There is poor charge and energy discrimination. Even though the track size and shape depends upon the charge and mass of the particles as well as the angle of incidence, there's significant overlap in the size distribution of the tracks due to the particles. And there's also variability in the solid-state nuclear track detectors. Environmental conditions and manufacturing procedures result in problems of precision and reproducibility from batch to batch. And there's a lack of theoretical understanding on how some materials are able to have tracks and others not. We weren't the first to do work with CR39 detectors. Other groups have done it. Richard Oriani and John Fisher published a paper in 2002 in the Japanese Journal of Applied Physics. In their experiments, they had CR39 detectors above and below their cathodes, and what they saw was that track density in their electrolysis experiments were significantly higher than in their controls. Andre Lipson and others did some work where they were electrochemically loading these heterostructures composed of gold, palladium, and palladium oxide with deuterium. And once they were done with those experiments, they took those cathodes out, placed them in contact with CR39, and cycled the temperature. And they saw tracks consistent with 2.5 to 3 MeV protons and 0.5 to 1.5 MeV tritons. They also did some in situ experiments using 50 micron thick palladium foil in contact with the CR39. These were light water experiments, and they showed that the tracks were concentrated in areas where the cathode was in contact with the detector. And they also did some experiments where they placed aluminum and copper spacer materials between the detector and the palladium foil and reported on the emission of 11 to 16 MeV alphas and 1.7 MeV protons. So this is our experimental configuration. We put the CR39 in close proximity to the cathode, and the reason for that is that charged particles can't travel very far in water. Here are linear energy transfer curves for these particles in water, and you can see that even if you have 10 microns of thickness of water, you can cut down 2 MeVs of the energy of the alphas. Our first experiment involved nickel screen in the absence of electric or magnetic field, and we did not see any particles. Instead, we saw the impression of the nickel screen. And I showed this to Stan, and he suggested, well, maybe what you're seeing is damage due to X-rays, because based on the work we did with photographic film and the earlier germanium detector experiments. So he suggested that we place our detector with another screen material in front of our XRD, and that's what we did, and you can clearly see the impression of the copper screen that was in contact with the CR39. And it's a lot sharper than what we see with ours, but here the XRD has a very coherent collimated beam, whereas with our experiments, our radiation emissions are in all directions, anisotropic. We did a similar experiment where we exposed the CR39 to a cesium source, and we saw the same kind of damage we saw with our nickel screen. So we believe this kind of damage is representative of X-ray and gamma ray emissions. However, when we put the nickel screen in a magnetic field, that's when we started to see the particles. Here you can see the outer eyelet of the nickel screen, and where the palladium plated inside the eyelet, you see a very high density of particles. This was a silver wire experiment that was done in a magnetic field. You see the damage is associated with the cathode. Now, this looks like an awful lot of damage, but you have to remember this experiment went on for 2 weeks, so everything is adding up in that 2-week period. At higher magnification, you can see we have small tracks as well as large tracks. Some of the tracks are elliptical in shape and some are circular. And we have these things called triple tracks. And this triple track was actually brought to our attention by Gary Phillips, who's retired of the Naval Research Laboratory, and we'll talk about that later, the significance of those tracks. But what Gary told us was that a triple track is indicative of a reaction that gives off 3 particles of equal mass and energy. So our features due to background or to a particle. So here on the left-hand side, we have tracks on CR39 that was exposed to an americium alpha source, and here's tracks from our co-deposition experiment. Here we have focused the optics on the surface of the CR39, and the tracks are dark in color. When you focus down inside, you see this bright spot in the middle, and that bright spot is caused by the tip of the cone acting like a little lens when the detector is backlit. And so dark on the surface, bright spot in the center, those are diagnostic features of a nuclear generated track. And you see we see the same things with our tracks. Dark on the surface, bright spot in the middle. Features that are due to background or chemical damage, are shallow, bright in color. They show no contrast. We did a series of control experiments. One of the things we did is we exposed our CR39 to our cell components in the absence of electrolysis. We let it go for the same amount of time as we did an electrolysis experiment. We saw no pits. So this told us that the tracks were not due to radioactive contamination of the cell components. We did electrolysis in the absence of the palladium chloride and saw no tracks. So this told us that the tracks were not due to the impingement of deuterium gas on the surface of the CR39. We replaced the palladium chloride with copper chloride in electrolysis experiments. There you have at the cathode metal plating out in the presence of deuterium gas. At the anode you have chlorine and oxygen gas evolution. The only significant difference is that palladium absorbs deuterium, copper does not. We saw tracks with the palladium system. We did not see any tracks with the copper system. So what this tells us is that the tracks are not due to chemical reaction of electrochemically generated deuterium, oxygen, or chlorine gases, nor are they due to the dendrites of the metal piercing into the CR39. We replaced the lithium chloride with potassium chloride and still saw tracks that told us that lithium was not required to generate the tracks. We replaced the heavy water with light water. We still saw some tracks with light water, but they were like 4 orders of magnitude less than what we saw in the heavy water system. And light water does contain deuterium in it, so it's quite possible that we're still seeing palladium-deuterium interactions. We also replaced the CODEP with the palladium wire. We did see some tracks with the palladium wire. They were not homogeneously distributed as we saw with the palladium chloride system, which told us that some sites of the palladium were more active than others, and this has been reported by other folks as well. And we did some experiments placing a mylar between the CR39 and a detector, and told us that the energies of the tracks were on the order of 1 MeV. And we also did some track modeling that supported those results. This is the results of the mylar experiments. Here we placed the 6-micron mylar between the cathode and the CR39 detector. So the CR39 detector is actually on the outside of the cell. The mylar will cut off 0.45 MeV protons, 0.55 MeV tritons, 1.4 MeV helium-3, and 1.45 MeV alphas. You can still see we saw tracks, and the fact that the CR39 is on the outside of the cell tells us, that, again, that the tracks are not due to chemical or mechanical damage. Okay, where I want to go. We did some track modeling. The track test program is freeware. It was developed by these fellows here, Nikizek and Yu. The input parameters for this modeling, you put in your energy of your alpha and MEV, incident angle between 30 and 90 degrees, your etch rate, which you can measure, which is in microns per hour, and the etch time in hours. And this is the relationship between the track etch rate to the bulk etch rate, and this is the equation that's used in the program. And here we modeled this particular track here. It's kind of like a pear-shaped track. If we put in an incident energy of 1.3 MeV, incident angle 35 degrees, etch rate of 1.25, and etch time of 6 hours, you get the same kind of pear-like shape. If you measure some of the parameters, D1 is the distance between the back edge and the bright spot in the middle. The computer analysis says it should be 5.59 microns. We measure 5.34, which is a pretty good agreement. The major axis, the computer says 9.32, we measure 9.36, and the minor axis 7.68, which is the same as what we measured. So it's pretty darn good agreement. To simulate the effect of water on the shapes of the tracks, we did an experiment where we took the americium source and we placed sheets of mylar between it and the detector. And in the absence of mylar, the energy of the particles on the order of 5.5 MeV, and you can see we have circular tracks as well as these elliptical and torpedo-shaped tracks. And those elliptical and torpedo-shaped tracks are coming in at an angle less than 90 degrees into the CR39. When you put an 18 microns of mylar between the detector and the americium source, the energy of the alphas has now been reduced to 1.92, and you can see we have primarily circular tracks. And that means that these tracks are caused by particles coming in at a 90-degree angle. These are the only particles that have enough energy to go through all that mylar. And it's the same effect we're seeing with our experimental electrolysis experiments because the particles have to go through water, and that slows them down. And here's the case if we have 24 microns of mylar, your energy of your alpha particles on the order of 1.09 MeV. And again, you see very circular tracks and some smaller ones as well. And here we compare our co-deposition tracks, seen here, with 1 MeV alpha tracks. You can see we have the circular ones, which we see in our experiments. And you see this one here looks very much similar to that one, and this track looks very similar to that one. And I'll turn the presentation on to Larry.
How do you advance here?
That one.
Okay.
Sorry.
You there? I'm Larry Forsley. I'm with JWK International, and we're a collaborator with SPAWAR. I've been following their progress for 20 years and became very actively involved in the last 4. A lot of the work that I've been doing with them has been in the nuclear diagnostics, looking at both charged particles and neutrons and gamma ray emanations. This particular slide shows a scan using a Tassel scanner for CR39. And what you see here is 1 millimeter swath of a piece of CR39 that is 1 centimeter wide and almost 2 centimeters long. So it's compressed in the Y direction. And on the front side, you see a series of tracks that are in fact coincident with 3 separate cathodes we had on there. We had a gold, a silver, and a platinum wire. On the back side, we also have tracks. Again, roughly coincident with the gold and with the platinum, but virtually nothing associated with the silver. And we discovered these by accident. Again, Gary Phillips, as Frank had mentioned before, he and I were scanning these with a Tassel scanner on the East Coast. And it turns out that day Pam was scanning some of these on the West Coast in San Diego, and within probably a few hours of each other, we had realized that we had been looking at the front and the back and unexpectedly found tracks on the back side. And the significance of this is that for a proton to go from the front to the back would require over 10 MeV. For an alpha particle to traverse this, it would take over 40 MeV. So the question became, if these are not charged particles, what's causing these tracks? Well, we have a second piece of information. If we look at the distribution, the number of counts versus the major axis of somewhat maybe elliptical tracks, we find that on the front we've got basically 3 populations. One which is around under perhaps a micron, one around a few microns, and the bulk of them are in a range of about 5 to about 15 microns peaking in here. From our calibrations, this area here more or less corresponds to perhaps a few MeV alpha particles. However, if you look at the distribution on the back, it's significantly different. You have 3 populations. You have a few of these small ones. You have a larger population here. But what's noticeable is this large hump that actually continues out past 40 microns. Now, if indeed this was caused by a charged particle going from front to back, generally the faster the particle, the more energy it has, the smaller the track it leaves. So a 40 MeV alpha is not going to leave a large track, it's going to leave a small track. On the other hand, these are consistent with having neutrons come in. And on my next slide, I'll show what this actually looks like. On the left-hand side, this is from plutonium oxide, which is a natural fission source, placed on top of a piece of CR39, and looking on the back side of it. So the neutrons are released, they pass through it, they interact with the carbon, hydrogen, or oxygen, they knock those particles through, and then when we etch them, as Pam said, you'll bring some of these tracks out. What's very noticeable, though, is all these smaller tracks. These are latent tracks. Because the efficiency of CR39 is so low for neutrons, on the order of 1 in 100,000, you can sequentially etch through, and you keep bringing up new tracks. These latent ones would become full-blown. You keep etching your way through. In our case, using a silver and palladium on the back side, you find the same kinds of tracks, and you find the same latent tracks in there as well. Now, there are basically three mechanisms by which these tracks can appear from the neutrons. Because the neutrons, being neutral, they'll just pass right through. They've got to encounter one of the atoms, and you can have an event here where you get a recoil where you'll hit, say, a hydrogen, you'll knock the hydrogen through, and the neutron will stall within. You can actually get a spallation. You can knock a proton out and pick that off, or actually have the carbon or oxygen come through. Or if you've got sufficient energy, what will happen is you'll hit, for example, carbon or oxygen, you'll actually shatter it, and you'll end up with 3 alphas coming off. If you look at a plot of the major axis versus the count, this is a log scale, it turns out you can do neutron spectroscopy this way. And again, this is from the work of Gary Phillips, who with DOE and Dikr funding went through and characterized these detectors to see if you could essentially identify different energy neutrons. And what you'll find is as the energy of the neutron goes up, you get larger tracks, and you have a region here which are due to recoil protons, a region around 25 microns, which correspond to recoil carbon and oxygen, and then there's a region around 35 microns, which is the 3 alpha breakup. And as I note down here, I can't read it from this angle. Oh, here we go. Gary's calibrated this from 114 kilovolts all the way up to almost 15 MeV. Now, if we superimpose the data that we've taken in our analysis, you find the following. Again, log of counts, the major axis across the bottom axis. So we take a 2.5 MeV neutron source, in this case a DD fusion tube, and a 14.8 MeV neutron source, which was spallation from a cyclotron. These are in red and in blue, and you'll find out that you've got a distribution. In the case of the 14.8 MeV, you actually have recoil carbon oxygen, but you have this peak down here, you've begun to shatter the carbon. If you look at ours from the palladium deuterium codeposition, we overlay on top of that, and in addition, we also have these peaks out here. Now, again, as I said before, one of the ways to confirm that these are in fact neutron recoils as opposed to some artifact is to sequentially etch. We normally etch for about 6 hours. In this case, Pam has etched for 60 hours, and we're actually going now for 53 microns of plastic removed, and these 2 latent tracks are beginning to come out, and this track that was closer to the surface is now getting much, much larger. And again, using the dual focusing, you can see these have the typical shape. And because these may be coming in normal, the neutrons may be coming in normal, but when you're going to have these scatter off, you'll have them going in almost any direction. And that's exactly what you see right here. These are consistent, in fact, with the neutrons you'd find from DD and DT fusion reactions, where in the case of DD, one of the channels gives you a triton and a proton, but you have another channel where you get a 2.5 MeV neutron coming off, plus a helium-3 with under 1 MeV. You have a DT reaction, which gives you a 14 MeV neutron, bracketed between roughly 12.5 and 15.5 in the data that we've taken. And we have a colleague, Andrei Lipsin, who took CR39 to a cyclotron in Russia and mapped out the energy versus the track diameter, and plotted these out. This is now just looking at protons. He then went through and sequentially etched this and found that although he couldn't easily differentiate these at say 6 to 8 hour etching, if you etch longer, you can in fact differentiate these, and that means you can differentiate protons in energy between, say, 1 and 2.5 MeV. Taking that data, he then produced a plot that shows the number of counts versus the recoil energy of the protons. And in this case, we're now looking at the recoils from the neutrons that came in and impacted CR39. And this particular data was actually taken at a co-deposition experiment done at SRI. First, he's overlaid on here a californium source, and that has a peak around 2.5 MeV, which is what's known for californium. It's a spontaneous neutron generator by spontaneous fission, and it has a tail that goes out actually as much as 5 or 6 MeV. What we see with the data from the CR39 from co-deposition is a nearly monochromatic source of neutrons because it cuts off very, very sharply above 3 MeV. Well, we've now characterized the potential that we've got DD fusion neutrons. Now we'll look at triple tracks. This is from the literature, and what happens is a neutron comes in. If it has over 9.5 MeV, it has enough to make up for the binding mass deficit between carbon-12 and 3 alphas. Any additional energy then goes into driving these alphas, and you can see that you get a variety of different positions. What's happening is the neutron comes in, and there's a tendency for it to go in the forward direction. But in fact, it will go off almost isotropically. You may have one of the alphas coming back towards you as you're etching. In addition, the CR39 plane that you're etching is here. You don't know where in the CR39 the neutron's going to impact it. So the distances and the angles that you get can be very arbitrary. If you look at our data, you'll find a whole cluster of potentially charged particles and neutrons. You'll find a triple track here. And these are from 4 separate experiments run, focusing on the top surface and then focusing at both the top and down at the tip where you're getting scattering. And you can see a variety of different shapes here. A little bit closer up, you can see again, you've got the 3 alphas coming off. And this is, again, very, very similar to what you find in the literature. Now, we can go one step further. We can now measure the distances in each of these. And if we come up with the rest mass difference, 9.6 MeV, and then we measure each of these distances and run them against the Let curve, in other words, how far an alpha of a given energy will go through CR39, we can then plot out each of these and come up with the energies of each of the alphas, and we come up with 12.33 MeV. Now, this is also an underestimate because, again, I don't know what angle theta is associated with each of these axes going back into the CR39. But consistently, the work that we've done has shown these to be between 12.5 and about 15.5 MeV. Now, taking the information that we've got and the observations we've taken you saw before, these ejecta cones are almost always 50 microns across in our case. If I calculate the volume, say I have a radius of 25 microns, and again, I'll underestimate and only say the depth is 25 microns. Given the melting point and the vaporization point of palladium, what I come up with is it takes on the order of 5.8 times 10 to the minus 2 joules to vaporize this quantity of palladium. If I assume I've got DD and DT fusion reactions occurring with the normal branching ratio of 50% into each of the 2 DD channels, then I would need on the order of 30 billion fusion events to vaporize this amount of material. Now, what's very significant about this is if you look at the CR39 we've got and what I showed before, you'll see that there are recoil tracks on the backside associated with the cathodes. If you add up all of the neutrons that we see times the inefficiency of CR39, we have on the order of 100 million to a billion neutrons that we see across the entire CR39. Yet what this is saying is that we've got on the order of 30 billion fusion events with 30 billion neutrons being produced. And the answer is that not all of this heat is being produced by conventional DD and DT fusion reactions. I would make the case that this is a strong example that there are at least 2 channels in this system. And looking at some of the possible nuclear pathways, I come from the hot fusion community in laser fusion. We start off with tritium, so you have a DT reaction to begin with, and you get the 14.1 MeV neutron. In fact, these triple tracks are referred to as nuisance tracks in the laser fusion community because you want to use the neutrons to diagnose what's happening in the core. So when you get triple tracks, they tend to obscure what other broadening of the track energy you've got. And we do the same thing. We're making use of the neutrons as a diagnostic to know what's going on inside the system. Running through the rest of these reactions, you come down to one mentioned before by Rob, that you get D plus D going to helium-4 about 10 to the minus 6 times, producing a gamma ray that's hard to see. And then we have another reaction, which is perhaps the thermal channel of cold fusion. This one produces only heat and has no gammas. So it may be that we have evidence of this happening in the system we've seen. In addition, there's a variety of tertiary nuclear reactions possible. If you've got energetic charged particles and neutrons, you're very likely going to get ash of some kind when these impact other things, both the charged particles and the neutrons, and in fact we've seen that in terms of the elemental transmutation. One of our colleagues, Mitchell Swartz, has gone and plotted out this data and come up with what he calls the optimum operating points, that there are points in terms of, in his case, electrical power versus the heat coming out, and for different ranges, for tritium, for heat, and for heat in the gas systems, you find that there are optimum power points to operate at. And this is one additional interpretation of the data, but if in fact this is correct, this would begin to give us a sense, there we go, would give us a sense of how to control the system. But what I'd noticed in some of our data and some of George Miley's data is there may in fact be a tendency to overshoot the optimum point, perhaps for heat or for charged particles. And at this point, I'll turn it back over to Frank.
Thank you, Larry. After we presented at the ACS meeting in March, some of the web postings said, "I'll believe it when it's been replicated." Well, these experiments have been replicated. In the case of heat and radiation, we've mentioned Mel Miles. In the case of tritium, John Bockrust, who is at Texas A&M. And in the case of energetic particles, Fran Tanzella from SRI, Winthrop Williams from Berkeley, and Ludwig Kulowski, who's retired from Montclair State University. And for 3 years, 2006, 2007, 2008, the senior class, the undergraduate class in the chemical engineering department at UCSD has to do a project, and groups of students there have selected these, and all 3 years they were successful in replicating the results. Mentioned 23 peer-reviewed documents. Those are comprised of 21 peer-reviewed journal articles and 2 book chapters. And you see here some of the journals we published in, and you know who else is published in some of these journals. We have a policy that we only talk about things publicly that we have published already, and so because the triple track data was published in January in Nature Wissenschaften, we were able to talk about that at the ACS meeting this past March, and that generated a lot of interest. Among the hot fusion and the physics community, there was a press release that the ACS produced. Local television, we were the top Yahoo News story for a few days. Drudge Report had it listed. Houston Chronicle, hundreds of newspapers picked up on the press release. The Economist did an article in a magazine. New Scientist online, Fox News online, hundreds of internet sites worldwide picked up on it. In addition, the Discovery Science Channel Brink called us and asked some questions, and they produced the following.
Here's a question for you. What's hot? Messy and impossible to control. If you said Amy Winehouse, you get half a point. I was kind of thinking more along the lines of nuclear fusion. Because this week, in what could, and I emphasize could, be one of the biggest breakthroughs ever, researchers from the US Navy's Space and Naval Warfare Center unveiled what they claim could be evidence of cold fusion, something that's never been done before. What's the huge deal with this? Well, fusion is what happens inside stars and thermonuclear bombs, right? When the nuclei of atoms join together. But it's really, really messy because nuclei have the same charge, so they repel each other, just like magnets. If I want to combine these 2 solid magnets into a single entity, I'm going to have to add massive amounts of energy and heat, and unfortunately, the killjoys at occupational safety won't let me build a coal-fired iron smelter here in the studio. But if we could somehow unite these repelling solids in a cool, controlled, low-energy environment, then fusion could produce unlimited amounts of clean energy, which is why it's been one of the holy grails of science. 20 years ago, a couple of researchers thought they'd cracked it. It was huge news back then.
What may be a tremendous scientific advance tonight in attempts to create and harness the almost limitless, clean power of nuclear fusion.
But that turned out to be just a false alarm. Which is it now? If it's real, it's one of the biggest breakthroughs ever. If it's not, well, at least we've still got Amy Winehouse, I guess. To sort this all out, joining me from Washington is Brink contributor, nuclear physicist and senior science advisor at the U.S. Department of Energy, Dwight Williams. Dwight, what exactly have these researchers done?
Well, it's pretty simple when you think about it. They took some electrodes, some nickel or gold electrodes, put it in a solution of palladium chloride mixed with heavy water. That's actually D2O instead of H2O. They ran a current through it, and the output that they got on their CR39 detection system indicated the evidence of neutron generation. And of course, neutrons are clear evidence of fusion.
What was the objective when they were starting out? Were they trying to create cold fusion?
Yeah, I think their intent was to create cold fusion, and so far the evidence does not discount that cold fusion was produced, but as of this point, all the jurors are still out as to whether this was indeed cold fusion. Simply the evidence of neutrons does not mean that fusion took place. There are other reasons why you might get the neutrons.
What else could they imply? What else might be going on here?
Well, it could be any number of things. Of course, as we mentioned, option A could be fusion. Option B, it could be some type of radioactive or chemical radioactive process that we don't even know about. This could be big in a discovery of that sense.
Now, as I understand it, one of the big problems with cold fusion has always been that, obviously, nuclei don't attract. They oppose each other because they have the same charge. How are they getting around that physical problem? And is this kind of a chemical workaround to that physical problem?
If this is cold fusion, then yes, it is a chemical workaround to the problem. And as of right now, no one really seems to have a firm grasp. There are lots of varying theories as to if this is indeed cold fusion, how they might be getting around this. But so far, there are lots of possibilities, but no definitive answers.
Now, you're a physicist. For you, surely one of the absolutes of physics is that if there are like charges, then they repel each other. Does that make you skeptical about the idea that this is possible?
Well, it doesn't make me skeptical. I would say there's enough evidence to support the findings. For example, it has been repeatable. According to the researchers, there are clear evidence of neutrons. So basically, I would say that I'm not skeptical. I'm not convinced just yet. If you go back 20 years to what ended up being a false alarm, you know, again, there are many yellow flags that came up immediately. Again, like I said, things weren't repeatable. Heat generation wasn't there. The neutrons weren't there. Normally, by this time, I would have been convinced that it's not fusion. But right now, I'm still able to be convinced.
Wow. So if it is cold fusion and it can produce energy into the future, is the power that it could generate limitless and clean?
Well, yeah, theoretically there's an upper limit. The upper limit would be the amount of water that there is in the ocean. Certainly.
That sounds like a pretty generous upper limit to me.
Yes, I mean...
Once we've exhausted all of the oceans in the world, we're not going to be able to use it anymore. What's that going to be? A million years, a billion years?
Exactly. Yes, and again, I mean, again, we're talking, you know, just plain old regular seawater would be all that we would need to generate the power. In addition, it's a clean energy, it's carbon-free, and again, there are no radioactive waste products because you're just dealing with varied forms of hydrogen.
So if this is cold fusion, there's no more worry about nuclear waste from nuclear power plants, there's no more worry about climate change and the greenhouse effect, we're sorted.
Yes, I mean, this would be the breakthrough that the world has been waiting for. This would be the source that actually powers all of the stars, able to be run on our very own power stations in our very own homes. We wouldn't have to worry about waste products. We wouldn't have to worry about anything for this generation or the generation to come.
It's amazing stuff. I'll be crossing my fingers. I guess you probably will be too. Thanks so much for your
Okay, I will tell you that in the preparation of that, they did not talk to us. They called us and we sent them some papers and then they put that together in about 2 days or a day and a half actually. So the capability they have for video is certainly very good. One of the things that Rob talked about was, some of the applications, and certainly heat is one of the applications, but high energy particles also open the door to a lot of other options. For example, as of 2007, the U.S. had accumulated more than 50,000 metric tons of spent nuclear fuel rods from the reactors. It'll take several thousand years for this to decay down to where it's not hazardous. But if you have neutrons that are greater than about 2.5 MeV, then you can fission the uranium in those fuel rods and not only generate more energy out of the fuel rods, but at the same time they will then be left as not hazardous material, and in fact ultimately you could use an external source of neutrons to design a fission-fusion reactor. Another application certainly is a green power source. This would certainly reduce, if not eliminate, the need to purchase foreign oil. Could eliminate use of energy as a source of conflict. In the case of California, we have a water shortage when we have the world's largest body of water, less than a few hundred yards from my office, and the only thing that's standing behind seawater and drinking water is power for desalinization, and certainly this could provide that. As far as the impact on the economy, the worldwide impact would be huge because all of a sudden it would be much more economical to redesign and invest money to take advantage of the low-cost power. And ultimately, designs for small power supplies. On the right, in the upper right, you see article that occurred in a Japanese magazine, and you see the lady has her little nuclear reactor right there in the kitchen with her. I'm not sure we're going to get there, but in any event, this was an interesting photo. Summarizing our experimental results, we've presented evidence of excess heat generation, evidence of low energy radiation emissions and X-ray and gamma rays, tritium production. We've presented results of the electric and magnetic fields and the change in morphology and transmutation. We presented results using the CR39 detectors and the fact that the energy levels that were measured in those detectors are consistent with DD and DT fusion reactions. So going back to March of 1989 and looking at where we are today, whereas there the experiments weren't repeatable, our experiments in fact are very repeatable. Where there weren't any refereed papers, there are many refereed papers now. We have 23 and colleagues in the field have also published. The experiments hadn't been replicated. Now multiple experimental replications have been performed. The question if it's nuclear, where are the neutrons? Well, we now have compelling evidence that there are neutrons. It doesn't match theory. Well, that's still the case. In fact, at this point, there are several theories that have been proposed, but we haven't seen any that would describe or predict all of the results that we've seen. And groups of scientists worldwide have, in fact, successfully performed experiments. So in conclusion, including production of nuclear events, including production of high-energy neutrons, can be triggered by electrochemical means, and there are lots of applications. Certainly more research is required to understand the phenomena, and new theories are evolving based on the experimental results. Next steps for us, we have not attempted to optimize the production of neutrons, and certainly if we're going to have a successful application using neutrons, then we have to be able to produce enough neutron flux over a long period of time to be useful, and that's something we need to work on. Also, continue the basic research into the underlying physics. Larry suggested multiple reaction paths, and certainly it would be nice to understand exactly what triggers each of those reaction paths so that ultimately we could choose. A debt owed certainly to Martin Fleischmann and Stanley Pons, who 20 years ago had the audacity to openly challenge what that all that was known about nuclear physics perhaps wasn't correct. Maybe they made some mistakes, but certainly it took a lot of conviction for them to stand up and make those claims. As Martin noted in 2007, he and Stan Pons had talked about many methods. They had thought about co-deposition, but thought it would be too hard. And so in that case, we would like to salute Stan Spock, who pioneered the co-deposition approach, because he didn't have the patience to wait for 2 weeks, and he's still impatient. I'd like to a debt ode to all of those who have continued to work in this field, even though it has been an area of research that is not necessarily career enhancing. To the SPAWAR management, who have allowed us to continue to work and publish in the field, and that's something that, again, you know, to the Navy and SPAWAR for allowing that, and certainly to your own Rob Duncan for reviewing the data for himself and reporting what he found. Let's see. Last week, Larry was in the UK and interviewed Martin Fleischmann. So hopefully we can.
The status is as before. We know a lot more about the system.
Let me. Okay. Yeah. You've seen Martin. He doesn't do a dance or anything. So if we can just get the audio up.
A very interesting discussion. I think it is the status is as before. We know a lot more about the system.
Okay, well, let me, unfortunately, it looks like we may not get to the final sentence that he said, which is one that I wanted to get, because his admonition to all of us was keep on going. So thanks to Martin. And for anyone who's worked in this area for a long time, anytime there's an article or a cartoon about cold fusion, they deliver it to you, and in this case, notice that they even personalized it for myself and Pam. And so, 60 Minutes folks, when they talk to us, ask about it, and I said, you either have to have a sense of humor or a real thick skin, and I think a sense of humor is far more important. So with that, if we have time, and my colleagues will join me, and there are any questions, we'll take a shot at them.
We get off easy today.
Yeah.
Well, I have a question for you folks then. From what you've seen between Rob and ourselves. What's that? Oh, I have a question for you folks out there then. From the talks that you've seen, Rob's and ours, how many of you believe there's something going on in here? Just show of hands. That's pretty good. Okay. How many of you are sure there's nothing going on? Oh, no, that's different.
Okay, well,
there's a question in the back.
Is there a question? No. Okay, well, thank you again.
Just waving at us.